Hi again, everyone. And in this lecture, we're going to take a look at reaction progress diagrams and the kinetic molecular theory of reactions. So before I start talking about reaction progress diagrams, I want to talk about the kinetic molecular theory of reactions. And yes, I will abbreviate here. So KMT, Kinetic Molecular Theory of Reactions. The kinetic molecular theory of reactions states that reactions occur when the following happen. Molecules collide with sufficient energy and proper orientation. Okay, so we, maybe I'll just make a little, get my model kit here and make just a little example here. I don't really know what I'm doing with this. It's just two different colored balls here. So these molecules have to collide. And maybe our reaction is we get one transferred to the other like so. So it ends up getting, make it like this, ends up getting stuck there. So in order to get that to happen, we have to have these colliding end to end. Okay, if they collide this way, well, that won't make the reaction happen. We can't get a new bond to form between this atom and that atom. Or maybe if they collide, kind of like this or like that. So we have to have correct orientation. We also need to have enough energy because, well, we have to be able to overcome the energy of the bonds that are being broken, and then we'll form new bonds. Okay, so what we can express this mathematically in the following way. So we can have something called the Arrhenius, or we have something called the Arrhenius equation. And that states that K, which is our rate constant, equals some factor, we'll just call it A, times E, the base of the natural exponent, to the minus EA over RT. And in this case, EA is the activation energy. R is the gas constant, 8.314 joules per mole Kelvin. And T is the Kelvin temperature. Huh, that looks interesting. That's kind of the same general format that we saw for delta G, or rather for KEQ, was E to the minus delta G over RT. You actually see this kind of equation pop up a lot in nature. This is one of my favorite equations. I don't know exactly why. I just like it. Anyway, what are the parts here? Well, our rate constant is going to be going to affect how fast the reaction occurs. We have our activation energy, which is the extra energy we need to add to get the reaction to occur. We have the gas constant, and we have temperature. So this actually shows that there's a temperature dependence to rate. And you probably experienced that in Chem 1B. I know you definitely did if you had me for Chem 1B. I actually went over the Arrhenius equation. Not all instructors do. Only those students who are fortunate enough to have an instructor that went over the Arrhenius equation are in good shape. Anyway, so R is the gas constant, T is the temperature. And then A is actually a constant which is takes into account the frequency of collisions, or rather the frequency of effective collisions. So sufficient energy is given by EA, and then A is going to be our proper orientation. All right, so let's take another look at this temperature dependence. So what I'm going to do here is make a nice big chart here, a nice big plot here. Okay, and so we're going to have our temperature in Kelvin, this axis. On the y-axis we'll have number of molecules. So let's say we have our reaction mixture at some particular temperature. And we have temperature. No, let's actually, sorry, this should not be temperature. This should be kinetic energy. Sorry about that. So let's say we have a particular temperature. Let's say 273 Kelvin. We actually find that, so we'll have our, we'll have some average energy for our 273 Kelvin. And let me draw what this should look like, something like that. So this is T equals 273 Kelvin. So we get a distribution of energy. And remember, if you think back to Kinetic Molecular Theory of gases from Chem 1A, temperature is a measure of the average kinetic energy of particles. So it's not the case that at 273 Kelvin, all the molecules are zipping around at the same speed. Some are moving really fast, have higher energy, some are moving really slow. A certain amount of them have enough energy that we can get the reaction to occur. Okay, so in this case, our activation energy is such that only this small portion have enough energy to occur. Most of the molecules here, so number of molecules, most of the molecules have less energy, and so when they collide, we're not going to get a reaction. Now let's heat things up. Let's heat things up to maybe, I don't know, maybe about like that. And maybe this is T equals, I don't know, 200 Kelvin. So we'll say, 200 degrees Celsius, so 473 Kelvin. And now we see that, because the activation energy for the reaction itself is the same, but now we've got almost half of our molecules have enough energy to get over the activation energy barrier here. Okay, so half of our molecules compared to, I don't know, 10% at lower temperature half of our molecules at high temperature have enough energy for the reaction to occur. And this is given in the Arrhenius equation. Okay, temperature is in the denominator of the exponent. So and it's a negative exponent. So a high temperature means a smaller overall exponent, but it's negative. So it's a less negative exponent, which would e to a less negative exponent would be a bigger number, so k will end up being bigger. It helps when you think about what the things mean mathematically when you, when you work out the whole equation. All right. Anyway, higher temperature reaction rate is faster. That makes physical sense. And this kind of diagram really shows you how it can make physical sense. But I did want to talk about reaction progress diagrams as well. So let's take a look at one of those. Okay, and actually we're going to look at a couple of them. So let's look at one of the reactions that we saw before. CH3Br plus Cn minus gives us CH3Cn plus Br minus. Just for fun, you guys can figure out what's the nucleophile and what's the electrophile here. So again, we'll follow our reaction progress on the x-axis, and we'll have energy, which I'll just call E, on the y-axis. So we'll start out with CH3Br and Cn minus, and we'll end up with CH3Cn and Br minus. And then we have some kind of hump here that we have to get over. Let's see if I can draw this reasonably well. There we go. So we start here, we have to get there, and this is what we have to get over. Now let's take a look at what's going on here. We've got a couple different colors here. So my delta G is this energy difference there. So this is my delta G naught. Okay, the energy difference between products and reactants. So this has a large negative delta G. So it's exergonic, I think believe is the technical term, but you can just think of it as being exothermic. And then when we go to measure the activation energy, our activation energy is measured from the low point, the previous low point, going up to the high point. So this is our E sub A. Excuse me. All right. Now, what's going on? Well, at the what do we have at the top? At the top, we have our transition state. TS. And in this case, what we'll have is we'll have a CH3 and we'll have a CN there. So I would draw it like that. I'll put it in brackets. So I have this weird species where the cyanide ion is coming in. And so I've got a delta minus there, delta minus there. The cyanide ion is coming in, and the bromine is being kicked off as a bromide ion. This carbon-carbon bond has not fully formed yet, and this carbon-bromine bond has not broken yet. This is a transition state, and transition states are not isolatable. And the typical lifetime of a transition state is less than the duration of one bond vibration. Remember infrared spectroscopy, we're looking at the vibration of bonds. Well, a transition state sticks around less than, or for less time than it takes for one little bond vibration to occur. It's around 10 to the minus 15 seconds. And we can't isolate these. We could create things that might be transition state analogs, but we can't actually isolate transition states. So this is a typical reaction progress diagram. Now there's one step here, and that's the Cn minus colliding with the CH3Br. It goes through this transition state, and we end up with our product here. We have delta G and we have EA. Now what about the other reaction that I showed? Let me just grab a couple more pieces of paper here. Now let me just grab all my paper. There we go. What about that other reaction? Let's take a look at it. So I've got CH3, 3CBr plus Cn minus goes to CH3, 3CCn plus Br minus. Sorry about that. All right, so let's see what's happening here. I've got my energy, got my reaction, and again I start with my reactants, CH3, 3CBr, Cn minus. And eventually I will end up with my products here, CH3, 3CCn and Br minus. And along the way, something interesting happens for this reaction. I actually undergo, not I, but the reaction actually occurs via two steps. So over here I have CH3, 3C plus, Cn minus and Br minus. So if I want to, oops, let me draw that out there. If I want to, I can look at the same parts of this guy. I still have delta G naught. And now I've got EA1, activation energy for step 1, and here I've got EA2, activation energy for step 2. So my two humps are my two steps in my reaction. The first step is bromine leaving, and it gives me these species, which are intermediates. In this case, I've got the 2-butyl carbocation as one of my intermediates. And these can be isolatable, and they do have a definite lifetime. Okay, so can be isolated sometimes, have measurable lifetime. Okay, we just know that for a transition state, the lifetime is less than 10 to the minus 15 seconds. We could figure out how long these intermediates actually stick around. So what's going on with this two-step reaction is we have our reactant here, and we go through a transition state, which is the CBr bond is starting to break. And then the bond finishes breaking and we're in the intermediates. We still have Cn minus, now we have Br minus, and we have the CH3,3C plus, the T-butyl carbocation. Now the T-butyl carbocation can bump into the Cn minus and we'll go ahead and get our final products here. Now, let me write this out here. Rate determining which step is going to determine the rate of the reaction? Well, it's going to be the step with the largest activation energy. And remember, you want to measure from the bottom of the previous low point. So EA1 is from here up to the peak. EA2 is from here, the energies of the intermediates, up to that second peak. So step 1, step 2. EA1 is bigger than EA2. Step 1 is the RDS in this case. Rate determining step. Now you could go on and have reactions that have many steps, and you'll see reaction progress diagrams with all kinds of steps. So you could have 3, 4, 5 peaks in your reaction progress diagram, and you'll need to be able to identify the activation energy, where the transition states are, where the intermediates are, what delta G is, figure out what the rate determining step is. All right, one last thing before we go, and I want to talk about catalysis. So catalysts will speed up a reaction, but they're not consumed in the reaction. And so sorry about that. Let's make this guy a little higher there. There we go. So let's say we have the following reaction progress diagram. So this is our uncatalyzed reaction. Catalysts typically work by lowering the activation energy. So now if I look at my activation energies here, I've got EA cat is less than EA uncat. Now sometimes it's not simply a lowering of the activation energy and the mechanism stays the same. Sometimes we might have, and I'm just going to, instead of writing it out, I'm going to show you, we might have a case like this. And this is what usually happens, or often happens, with enzyme catalysis. We actually see that we have one pathway for the uncatalyzed reaction, but then, or one mechanism for the uncatalyzed reaction, but then a different mechanism, a different reaction pathway for the catalyzed reaction. So we've got all these bumps here. Now, let's just take a look at this and see which of these do we think is the rate determining step. And let me get my ruler out here. And so it looks like this first step here is 5 millimeters. Okay. Second step, I want to go to the top there, and then the bottom of the guy in front of it says 12 millimeters. This third one, again, I want to go to the top of that one and the bottom there, 10 millimeters. And it's about 7 or 8. So it looks like this second step here is the rate determining step. Okay, so your rate determining step is not necessarily your first step. It could be any of them. And I'll give you a hint. It's not necessarily the highest peak. It's the highest local peak, if you will. You have to have that greatest activation energy. So the difference from here up to there, or looking from there up to there, or there up to there. You don't want to be measuring just from, just from the overall bottom, let's say. Anyway, we can talk more about that in person, but I did want to go over reaction progress diagrams, talk about how reactions occur, how temperature can affect reactions, and yeah, you guys can enjoy that. Let's see if there was anything else I wanted to mention. We're not going to worry about section 6.11, comparison between biological reactions and laboratory reactions. I mean, it's kind of interesting stuff, but it won't be on the quiz or exam, so feel free to read it if you want. But in the meantime, focus on, what I'm telling you about reaction progress diagrams. Give the practice problems a try, both end of chapter and the practice problem set, and I'll be posting a practice quiz soon as well. All right. Until next time, stay safe out there. Bye now.